Welcome, honors chemistry students. This is our remote learning program, and welcome. So today we're going to actually begin chapter 13. So one thing that I would like you to do is, as always, I would like you to take very good notes. I'm going to be notating things on the screen for you and talking about things that you should write down. So today we're going to begin states of matter, and 13.1, which is also on Moodle for you under the PowerPoint section, is the nature of gases. So first off, every one of us has listened to the weather, and we've heard them talk about atmospheric pressure is at so many millibars, and temperature, and those things are what we have come to expect to hear from the weather person. But what does that exactly mean? What factors most strongly affect our weather? So we're going to look at gas and how, in fact, we have pressure, and specifically the atmospheric pressure. So first off, we got to talk a little bit about gas, the kinetic theory and the model for gas. There are three assumptions, and I would label in my notes 1, 2, 3, and this is about the kinetic theory right here. And we've talked about kinetics before, kinetic and potential energy, so you're familiar with that concept. Kinetic is motion, the particle motion, energy that is with motion. So let's define it here, and that's a word that you should get into your notes: kinetic energy. The energy an object has because of the motion. So we are not talking about potential or stored energy. We're actually talking about movement. So kinetic energy is the energy an object has because of its motion. So that's the first term that you should jot down in your notes. So the kinetic theory, it has three parts, and we're going to highlight those three parts and label them 1, 2, and 3, and you'll get some notes in on that. All matter consists of tiny particles that are in constant motion. So we know that as atoms. We studied that in several chapters, but we're going to look specifically now at the atoms that pertain to a gas, or we could also say the molecules of a gas. The particles in a gas are usually molecules. And we know they're atoms when in fact they're the noble gases, which we have talked a lot about. So first off, our first point, and I would label this point number 1. The particles in a gas are considered to be small, hard spheres with an insignificant volume. What does that exactly mean, a small, hard sphere? Well, that's talking about the nucleus. That's where the protons and the neutrons are. And when we say insignificant volume, we realize and know that they are minute. They are really, really tiny. And that's where Avogadro's number came in from the last chapter, 6.02 times 10 to the 23rd. So when we talk about a gas, these particles are far apart. And between them is a lot of empty space. And there is no particle attraction. And that's why, in fact, it is a gas, is there's no particle attraction at all. So they're not going to be able to come together. And if they did come together, we'd have a liquid. So knowing that is why we can say the particles in the gas are considered to be small, hard spheres with insignificant volume. That's our first point. Number 2. So the motion of particles in a gas, it's rapid, constant, and random. So we know that particle motion does not stop. We're not at absolute zero, which is 0 Kelvin. So we always will have motion. When we talk about a gas, there's no attraction. So these particles are going very quickly in all directions. And that is why a gas can fill its entire space and the container that it would be in. So we don't have a particular volume, and there's really no particular shape. And that's what this right here is notating to us. So that's our second point. The motion of particles in a gas is rapid, constant, and random. Well, we realize that if it's in a container, it is going to be striking the containers and bouncing back. There's no way for it to escape. That's why we have it in a container. So that still falls along the lines of motion is constant, rapid, and random. So when we talk about this motion, it is in a straight line. So we want to make sure we notate that it isn't a straight line until it strikes something. Now, if it strikes and it's moving straight ahead like so, and it strikes a wall, it's going to bounce straight back. But if it hits a wall at an angle, it is going to ricochet at that angle, going in the opposite direction. And that is called the collisions are elastic. It's an elastic collision. So that brings up our third and final point, and this would be labeled number 3. All collisions between particles in a gas are perfectly elastic. So that means the energy is conserved. So I want you to make sure you notate that. When we talk about an elastic collision, the kinetic energy that the particle had before it either struck the wall or another particle is going to be completely conserved. It is not lost. So the energy it had, it will maintain the speed, the velocity that it has will be maintained after it strikes and leaves. So there is just transfer of energy. It is not lost. So the total kinetic energy remains constant. So just to reiterate our 3 points. Point number 1, all atoms are made up of these small, hard spheres with insignificant volume when we talk about gases. They're atoms or molecules. Number 2, their motion is constant, rapid, and random. And number 3, the collisions are perfectly elastic, meaning there is no loss in kinetic energy. So our first checkpoint question, describe an elastic collision between gas particles. So if you would pause this video for just a second and think about how we would answer that. All right, hopefully you took a second to think about that answer. And an elastic collision is one in which kinetic energy is transferred from one particle to another with no loss in the kinetic energy. All right, so we're going to talk a little bit here about gas pressure. How does kinetic theory explain gas pressure? All right, so first off, gas pressure results from the force exerted by gas on an object. Moving bodies exert force when they collide. So think about the pressure you have all around you. Or for that matter, if we have a balloon. If we had a balloon in our hand, there is pressure, atmospheric pressure that's being forced all around it. And that is why the balloon is not inflated. It can't just naturally inflate. You have to provide a force into that balloon for it to blow up. And the force has to be greater than the force of the atmospheric pressure of the gas molecules that are surrounding that balloon. So let's get another definition. So gas pressure. Gas pressure is the result from the force exerted by a gas per unit surface area of an object. So I would get this right here into my notes. So the key concept, gas pressure is the result of all these molecules or atoms that are colliding with an object. So when we think about everything that we are aware of, there is pressure because there's gas all around us, here on Earth that is. But if you go to space, now we have a vacuum and there is no particles, so therefore there's nothing striking an object, and therefore we have something called a vacuum. And this is another definition for you to get down in your notes. An empty space where no particles and no pressure is called a vacuum. Now we can create a vacuum in some situations here. We have a vacuum pump here in the lab that when we get back together, I will definitely show you, but that is removing the particles so that there is no gas and therefore there would be no pressure. And that is a vacuum. So when you think about this, an astronaut, when they go to space, they have to wear a suit. And think about why that is that they have to wear a suit. And secondly, not in dealing with air pressure or gases, think about a diver that would go down in the water. And we're going to come back to that here in a few minutes. So first off, air exerts pressure on Earth. We know that. And that's because gravity. Gravity is pulling down and it is trapping these within Earth's atmosphere. You guys are very familiar from physics, 9.8 meters per second. That's the force of gravity. But now we're talking about it trapping the gas particles here. So when we talk about what is atmospheric pressure, and here's another term I would ask that you please get into your notes, and I've highlighted it there in red. The collision of atoms and molecules in air with objects, including you as an individual, is called the atmospheric pressure. So that is a result of all the air molecules that are around us. The next point is something that we're going to talk a lot about when we get to boiling point, when we talk about liquids. But atmospheric pressure, as you go up in a mountain, you know, if you're in the mile high city, you are 1 mile above sea level. So that means the air is thinner. So there's less particles there. And that would mean there in that part, you would have less atmospheric pressure. So that is the point that this section right here is making. The atmospheric pressure decreases as you climb a mountain because the density of Earth's atmosphere decreases. So you have less oxygen as you go up. And that's one of the reasons you've heard me mention previously that athletes go to Denver, Colorado to practice, because now there's less air pressure, which means less oxygen. So that way they get used to that environment and it builds their stamina. All right, a barometer. So let's talk about a barometer. That's another term you should get in your notes. A barometer is a device that measures the atmospheric pressure. Now, they're not as common as they once were. If you go over to your grandparents' house, you may, in fact, see something that looks like this. This is a barometer that was classically used quite a number of years ago, but it told the time of the day. It also told the temperature outside and the pressure. And it was used for lots of different purposes, whether it was to go fishing or whether it was to know whether or not a storm was going to come in. And that is a picture of a barometer. So back onto barometer, and why is it important? Let me back up a slide here. At sea level, air exerts 760 millimeters of mercury. And that's one of the units that we're going to be talking about and learning how to convert between. But if you go to a high mountain, now it falls to 253. So you see there's a huge difference, 253 versus 760. And that comes back to the less air particles as you go higher, and therefore pressure. But right here is a barometer, a homemade style of a barometer. And all that it is a dish. And they use mercury because mercury is very dense. You could actually use many other different substances. But what they do is they fill this column right here. They fill it all the way to the top with mercury. And then they have some sort of a dish, which is represented right here, with mercury already in it. And then they carefully take it and then they tip it into that mercury dish, not allowing any of the mercury from the column to come out. What happens is the mercury gets trapped, and what gravity does is pulls it down, creating an area up here that is a vacuum. There is no air particles. Now, what is holding this mercury up? As you can see, it's quite high on this little glass tubing. And that is because gravities and pressures push right there down on that. So the higher the pressure being pushed down, the more that it holds it up. So when we talk about at sea level, we're typically talking about the force of the air pressure pushing down is 760 millimeters. So where's that 760? It is right measured there. That distance right there is your 760 millimeters. So depending on the atmospheric pressure, you could be higher than 760 or lower than 760. And that's what's the case when we talk about being on top of Mount Everest. It's less pressure pushing down. So therefore now you are only at 253 millimeters of mercury rather than the 760. So, and that's what weather people talk about. So if you have a low pressure system coming in, that typically means you're going to have a storm. So what units do we as chemists use to measure atmospheric pressure? Well, here is the SI unit is pascals, and that's important, but that's not the one that we're going to be using in chemistry. The one that we're going to be using in chemistry is kPa, or kilopascals, and that is the number that is going to be significant for us. There are two other units. Actually, there's really three other units that are used a lot. That's millimeters of mercury, atmospheres, and something called torr, T-O-R-R. And that is probably you used in physics last year, torr. And we're going to talk about the conversions of that. The most common ones that we'll use is atmospheres and kilopascals. All right, so one standard atmosphere, so ATM, an atmosphere, we talked about atmospheres briefly earlier when we said standard temperature and pressure, standard temperature and pressure. And we said the standard pressure was 1 atmosphere. So let's talk about what that is. One standard atmosphere, or known as ATM, and that's another vocabulary term for you, is the pressure required to support 760 millimeters of mercury at 25 degrees Celsius. All right, so here are the conversions, and these conversions are very, very important. We're going to actually start to practice using these right here. So in my notes, I would highlight that. I would write 1 atmosphere is equal to or proportional to 760 millimeters of mercury, which is also the same as 101.3 kilopascals. So all of those terms are equal. If I brought torr into the mix, which I mentioned a few seconds ago, that also equals 760 torr, though. That's the unit for that. So we have all of those equal, and we've already learned how to make a ratio, and that is how, in fact, we're going to solve between any of these units. So 1 atmosphere equals 760 millimeters of mercury. It equals 101.3 kilopascals, which also equals 760 torr. So let us look at this. So first off, we're going to do an example problem here. Now, you know that our PowerPoints have a lot of examples in them, and they show you, for the most part, the exact same way that I teach you to do it. So we're going to look at, if you had a pressure gauge that registered 450 kilopascals, how can you convert that? How do you convert that to atmospheres or millimeters of mercury? And we're going to try and do part A first, which is converting to atmospheres, and then we're going to convert that same number to 450 kilopascals. So I have a blank screen here, and what I'd like to do is begin the process of writing this for you. So first off, let's write down our relationships here. So we have 1 ATM, and it is equal to 101.3 kPa, or kilopascals, which is equal to 760 millimeters of mercury, which is also equal to 760 torr, and that is a 60. All right, so with that, gauge right there, let's break down the first one. So it gave us that we have 450 kilopascals, and it wants us to convert to millimeters of mercury. So first off, in order to do this, we need to set up and make a ratio. So when we look at our chart that we have just placed right here, we see that we could rewrite this, in fact, that 760 millimeters of mercury over 101.3 kilopascals. And that is exactly how we're going to solve this problem right here. So we are going to go 450 kilopascals and place that over 1. We're going to go our conversion factor, which we just wrote right here, and we're going to go 760 millimeters of mercury and divide that by 101.3 kilopascals. And we'll grab our calculator and we'll plug this in. So we go 450 divided by 101.3 and multiply that by 760. And we come up with a number that looks like this. 3376.11. Well, we only have 2 significant figures. Only 2 significant figures are given to us, so therefore we must round this. So what we're looking at here is that is 76 right here. So we have 3,400, and this would be our unit, millimeters of mercury. We could also write that in scientific notation, and we could do, or right here, 3.4 times 10 to the 123 of mercury. So either one of those 2 answers would be acceptable. All right. The next thing it was asking us to convert that 750 to atmospheres. So let's set that up as well. So we have 450 kilopascals, and we're going to place that over 1. And now we have to make another conversion. So let's just put our line right here and realize we have to have kPa on the bottom, and we have to have atmospheres on top, because that's what it's asking us to convert. So when we look at this unit right up on the top here, let's highlight what we have to actually use. So we have kPa, which is right here, and we have atmosphere. So it's 1 to 101.3. So let's fill that in. 1, and here is 101.3. And now let's plug that into our calculator. So grab our calculator, 450 divided by 101.3. And we come up to 4.44. 4.44. And that is ATM. But we have only 2 significant figures, so we have to put that to 4.4. So let's write that down, 4.4 ATM. And that right there is our final answer on that. So now let's look at the PowerPoint. You guys know that I always like to break it down and show you the process, and that's what we're going to look at, how they do it on the PowerPoint. So as always, they write down everything that they know, and then here are what is being asked to convert to, and they've made their ratios, and you can see their ratios right here, very similar to what I just did on the previous slides. And here they set up the cancel, so the canceling doesn't stop. Set up the cancel, and then your units are at the top. And you must always remember significant figures, and that is what they've taken for account on these as well. All right, so what is the pressure in millimeters of mercury inside a vacuum? So remember, think about that. Vacuum, think of space. What is that? Well, you should have come up with something like that, a 0, and that's what it has there, 0. Okay, so now we're going to continue on, and we have another key concept here. What is the relationships between the temperature in kelvins and the average kinetic energy of particles? So before we actually do that, let's just back up once more here to this slide. And we see that it says 0. So let's talk about something I had mentioned previously. You see here on this slide, let's go to this. Here's another look at the millimeters of mercury of how they make the barometer. And once again, you could do this with water, but if you had water, this column right here would not be just 760 millimeters, and that is millimeters right off of a meter stick. If you used H2O, so you have water in some kind of a tube, it is going to be roughly 34 feet high. So that's why it's not really practical to use plain water to test atmospheric pressure. But these are two common things that we know about. So here on the left, you see a spacesuit. Why do they have to have a spacesuit? Well, if they're in outer space, it is a vacuum and there is no particle pressure. There's no pressure at all. So there's no air, there's no particles. So if they did not have this, what would push in on their body? So they have to create an atmosphere, and that is what that very thick, heavy suit is doing. It's providing pressure to replicate the pressure here on Earth. If you look here on the right, that is dealing with intense water pressure. So if you go very deep sea diving, this is an apparatus that was used years ago. It's along the lines of the same principle. The pressure is pushing in on them, and they have to have something to force back out, and that's why you have this steel helmet to allow for them to survive and go to certain depths. All right, so with that little example, we're going to continue on. So what is the relationship between temperature and kinetic energy? So if you remember back quite a number of chapters ago, we defined kinetic energy and potential energy. We said that potential was stored in position in bonds. We talked about kinetic energy, and a measurement of the average kinetic energy was temperature. And that's what we're going to relook at here now, and actually realize that it's the Kelvin temperature that is the relationship. So if we talk about absorbing energy, that means the particles are going to be moving faster. Same thing if you heat something on a stove, you're actually putting energy into that substance, causing the particles to move faster. And the same thing is applying when you talk about a temperature. The temperature of the air, if you raise that, now we have more kinetic energy. And this is the average of the kinetic energy is what the Kelvin temperature is. So the average kinetic energy is measured in Kelvin. And that's the K term. And there's no degrees. There's no little degree sign like Celsius has. It's just plain kelvins. Now remember, there's never a negative Kelvin. 0 is the absolute lowest you could possibly go, and never has happened, but it is the lowest you can go. So at any given temperature, the particles of all substance, regardless of the physical state, have the same average kinetic energy. And this is a very important concept. So if you talk, it doesn't matter what substance, if you have the same temperature, they have the same average kinetic energy. So I would jot that down. I make myself a little side note of that and say average kinetic energy, same temperature, same average kinetic energy. And we talk about average, you got to remember a bell-shaped curve. And the average would be about right there in the middle. Now you're going to have some particles with more, some particles with less. And I could say plus and some minus, and then here is your average. And that's what this graph is showing right here. And this is standard distributions and distribution curves. So if you talk about lower temperatures, say we're talking about some cold water here. So the average kinetic energy of the particles is going to be somewhere about there. If you have this certain temperature, it's much higher in hot water, it's going to be around about right there in the center of that line. And now you have a bigger distribution. Why? Because you have a higher temperature, a higher degree. So therefore you have more on either side of the curve. All right. So let's continue on here. So absolute zero, you heard me mention that, it's 0 Kelvin, or you could say negative 273.15 degrees Celsius, and I just circled that for you. That is theoretical. It's when all motion ceases, and that's absolute zero, and you should be familiar with that. Absolute zero has never been produced in a laboratory. Now, there are some areas space-wise it's thought to possibly occur, but it has not been accomplished here on Earth. The coldest temperatures recorded in outer space are not in a laboratory, they're from outer space. About 1 Kelvin is what it is hypothesized. Perhaps lower, perhaps even down to 0 Kelvin, but that is measured with a radio telescope. So what is the accuracy on that? Well, not 100% sure, but it's not going to be as accurate as we would be here in the lab. The average kinetic energy in Kelvin. The Kelvin temperatures of a substance is directly proportional to the average kinetic energy. So what is the result of increasing the temperature of a gas? So if you take a gas and you raise the temperature, what is happening to the kinetic energy? So does it decrease? Is there no effect on the sample? Is there an increase, or do the particles slow down? Take a second and try and come up with an answer on that. All right, if you chose C, hopefully you did, you have the right answer. So an increase in the average kinetic energy of a sample. That's what happens if you increase the temperature. And ladies and gentlemen, that is this lesson. So the back of the PowerPoint slides all have your key concepts. And then we have had several vocabulary words in this section: kinetic energy, kinetic theory, gas pressure, a vacuum, atmospheric pressure, and barometer. Pascal, kilopascals, talked about torrs, millimeters of mercury, standard atmospheres, and that is the end of 13.1. So thank you for watching. Be sure you check out the daily bell work that you need to reply to. Go in peace.